On September 23, 1999, a spacecraft reached Mars after traveling through space for more than 9 months. Its engines fired exactly on schedule. The spacecraft began passing behind the planet, just as mission controllers expected. Then its signal disappeared 49 seconds earlier than predicted. Controllers waited for the spacecraft to emerge from behind Mars. The signal never returned. NASA had lost the Mars Climate Orbiter, not because its engine exploded, not because Mars produced an unexpected storm, and not because the spacecraft suffered a mysterious hardware failure. It was lost because 2 computer systems did not agree on the meaning of a number. One system produced data using pound force seconds. Another expected Newton seconds. The difference was a factor of 4.45. And across millions of miles, that small disagreement sent the spacecraft fatally close to Mars. The Mars Climate Orbiter had launched from Cape Canaveral on December 11, 1998, aboard a Delta II rocket. Its mission was ambitious. It would become the first interplanetary weather satellite, studying the Martian atmosphere, climate, dust, water vapor, and temperature. It was also designed to act as a communications relay for the Mars Polar Lander and 2 small probes arriving later. For most of the journey, the mission appeared healthy. The spacecraft communicated with Earth, responded to commands, and continued toward its planned encounter with Mars. But reaching another planet is not simply a matter of pointing a spacecraft in the correct direction and waiting. During the journey, engineers must constantly estimate its position and velocity. Even tiny forces can slowly change the trajectory. Sunlight pressing against a solar panel, small thruster firings, and the movement of onboard equipment can all influence where the spacecraft will arrive months later. The Mars Climate Orbiter used spinning reaction wheels to control its orientation. Over time, sunlight caused momentum to build inside those wheels. To prevent them from reaching their limits, the spacecraft periodically fired small thrusters. These events released the stored momentum and allowed the wheels to continue operating normally. Each individual firing was extremely small, but navigation engineers still needed to know exactly how much force every firing applied. That information was processed by ground software and transferred to the navigation team. The interface specification required the values to be expressed in Newton seconds, the metric unit of impulse. But the ground software produced the data in pound force seconds. The navigation software received the numbers and assumed they were already metric. No automatic warning appeared. No message said that the units were different. The file looked normal. The numbers were simply interpreted incorrectly. Because 1 pound force is approximately 4.45 newtons, the navigation system underestimated the effect of every small thruster firing by that same factor. Imagine receiving a distance marked as 100 and assuming it means 100 kilometers when the person who sent it meant 100 miles. The number is not obviously wrong. The meaning is. That was the danger aboard Mars Climate Orbiter. The error did not create one dramatic course change. It created many small inaccuracies that accumulated throughout the 9-month journey. And the spacecraft was performing these momentum control firings far more often than the navigation team had expected. Its asymmetrical solar array caused momentum to build more quickly, so the small thruster events occurred approximately 10 to 14 times more frequently than anticipated. That meant the unit error was being repeated again and again. The navigation model believed it understood the spacecraft's movement, but the real spacecraft was slowly separating from that model. There were warning signs. During the spring and summer of 1999, engineers noticed differences between expected and observed tracking data. One method of calculating the trajectory repeatedly suggested that the spacecraft was approaching Mars lower than predicted. Concerns were discussed informally, but the discrepancies were never fully resolved. A direct comparison between the velocity information calculated on board the spacecraft and the data being used on the ground could have exposed the unit mismatch. That comparison was not completed in time. On September 15th, the spacecraft performed its final planned interplanetary correction. The goal was to place its closest approach to Mars at approximately 226 kilometers above the planet. That altitude would allow Mars to capture the spacecraft without pulling it dangerously deep into the atmosphere. But during the following week, navigation estimates began falling. First, the predicted closest approach dropped into a range of approximately 150 to 170 kilometers. Then, about 1 hour before arrival, the latest calculation suggested the spacecraft might pass as low as 110 kilometers. The mission's engineers believed the minimum survivable altitude was around 80 kilometers. The estimate appeared uncomfortably close, but still above that limit. There was a possible final defense. A contingency maneuver, known as Trajectory Correction Maneuver 5, could have raised the spacecraft's path shortly before arrival. The maneuver was discussed, but the team had not completed the planning, testing, decision criteria, or procedures needed to execute it confidently under pressure. The onboard timeline for entering Mars orbit had already begun. The correction was never performed. At 9 hours, 0 minutes, and 46 seconds UTC, the main engine started its Mars orbit insertion burn. For several minutes, everything appeared normal. Then, at 9 hours, 4 minutes, and 52 seconds, the signal vanished. It happened 49 seconds earlier than expected. Controllers anticipated that Mars would block the signal for approximately 21 minutes. They waited for the spacecraft to reappear on the other side. Nothing returned. Teams searched for the signal for days. They considered different frequencies, emergency modes, and possible trajectories. Mars Climate Orbiter was never heard from again. Only after the loss did investigators correct the small force calculations using the proper units. The new estimate placed the spacecraft's closest approach at approximately 57 kilometers above Mars. That was far below the altitude considered survivable. The spacecraft most likely entered too deeply into the Martian atmosphere and was destroyed. Another possibility was that it passed through the upper atmosphere and escaped back into orbit around the Sun. Either way, the mission was gone. The investigation quickly found the pound force second and Newton second mismatch. But NASA officials emphasized that the deeper failure was not simply that someone had used the wrong unit. People make mistakes. Complex projects are supposed to contain systems that discover those mistakes before they destroy the mission. Here, those defenses failed. The software interface document specified metric units, but the ground software did not follow that requirement. The mistake was not found during design reviews, code reviews, testing, or validation. The navigation team did not have enough familiarity with important characteristics of the spacecraft. The teams responsible for spacecraft operations and navigation did not communicate their concerns effectively. Some anomalies were handled through informal messages, instead of a formal system that would force the problem to remain open until it was resolved. The navigation team was also understaffed while supporting several Mars missions. Independent review of the critical navigation analysis was insufficient, and the team was not prepared to execute the final correction maneuver that might have provided one last chance. The Mars Climate Orbiter was not lost because one person forgot how to convert pounds into newtons. It was lost because a wrong number passed through an entire organization without being challenged strongly enough. A software file contained the error. Communication allowed it to survive. Testing failed to expose it. Repeated small forces allowed it to grow. And incomplete contingency planning removed the final opportunity to correct it. The story is often used as a joke about Americans refusing to use the metric system. But that version misses the real lesson. The problem was not that two measurement systems existed. The problem was that a critical interface depended on an assumption, and no system successfully verified that the assumption was true. In engineering, a number without a unit is not complete information, and in a complex system, an unchecked assumption can travel much farther than any spacecraft. Mars Climate Orbiter crossed millions of miles successfully. It survived launch, deep space, radiation, and 9 months of operations. But it could not survive one misunderstood number. Every great system has a hidden story beneath the blueprint. Subscribe for more engineering failures, expensive mistakes, and decisions that quietly changed our world.